Hello, Course 2 students. I miss you guys. Here's a quick video on section 7.1.4 that will especially help when you get to, I believe it's problem 45. If you have any trouble with that one, here's some examples to help out. So we've talked about continuity in the past, and the definition we gave for continuity before was right here, a continuous function that can be graphed without lifting your pencil from the paper. So basically, if you have a graph that doesn't have any breaks or gaps in it, then we call that a continuous function. But now we're going to look at the more formal definition, an algebraic definition using limits that says in order for a function to be continuous at some point C, f of C needs to exist. The limit as x approaches C needs to exist. And then these two things need to be equal to each other, which is stated in the third step. So it's a three-part test. And so we'll go ahead and look at some examples of how we can use that formal definition to show that a function is continuous at a given point. Okay, so let's look at example A. We have f of x equals 2 over x minus 5. And so graphically, we can just draw a quick sketch and we'll see, let's see, this has a vertical asymptote at x equals 5. And this is just a translation of y equals 1 over x. And so its graph would look like this. The 2 on the top just creates a vertical stretch, so that doesn't really change the shape too much. So our graph's going to look like that. So we can see from the graph, there's definitely a break at x equals 5. We cannot possibly trace this curve with our pencil without lifting it up as we move along. If we're tracing here, we have to lift our pencil then to continue tracing on this part of the curve. So there's definitely a discontinuity at x equals 5. We see that on the graph, but the question is now, how do we show that using this three-part definition of what continuous means? So we want to show that one of these things must fail because we can tell from the graph that it's not continuous. So let's look at part 1. Does f of c exist? If I try to calculate f of 5, that would be 5 minus 5, so 2 over 0. That is undefined. So we say f of x is not continuous at x equals 5. So we're not continuous at x equals 5 since f of 5 does not exist. Okay, so step 1 up here, requirement number 1, all three of these things have to be true, and we failed on part 1. And so since part 1 isn't satisfied, we can say this function is not continuous at x equals 5. Okay, let's go ahead and take a look at example B. So this one, if we try plugging in x equals 3, or actually let's think about what's going on with this graph. If we factor out an x, we have x minus 3 over x minus 3. Now it's not okay to cancel those. We cancel common factors inside a limit, but if I cancel those, I'm basically removing the discontinuity. And so we see that we cannot plug in x equals 3 for the same reason we couldn't in example A, because the function is undefined there. So this one's also going to fail at step 1, but it fails in a different way. Instead of having an asymptote, when we do cancel common factors, we just have the function g of x equals x. And so that's just the line y equals x, but there's a hole when x equals 3. So if we graph the line y equals x, and then we put a hole here at x equals 3, that's the factor that we canceled out. So whenever we have common factors in the numerator and denominator, that creates a hole. So this one has a discontinuity also. We can see when we're tracing along this graph, we have to lift our pencil when we get to the hole to get to the other side. And anytime we have to lift our pencil, there is a discontinuity. And the reason, again, is step one failed. So we can say g of x is not continuous at x equals 3, since g of 3 does not exist. It's undefined. And we see from the graph there is no point right there where the hole is at x equals 3. So this hole would be at the point 3, 3 on this graph. Okay, then let's look at example C. So think about this graphically. This is just a parabola shifted up 3. And parabolas go on forever and they don't have any breaks in them, so this one should be continuous. Now the task is to just show algebraically why it's continuous. And so step 1, f of 2, or h of 2 is equal to 2 squared plus 3, so that is 7. Step 2, does the limit as x approaches 2 of x squared plus 3 exist? And yes, it does. As x gets close to 2, this graph gets close to 2 squared plus 3, which is 7. So this limit is equal to 7. And now we see that these two are the same, so that satisfies step 3. H of 2 is equal to the limit as x approaches 2 of h of x. So all three conditions are met, which means h of x is continuous at x equals 2. And so we can see this parabola, if it continued on 1, 2, 3, 4, 5, 6, 7, it would go through this point right here. And so it passes right through the point 2, 7 without having to lift our pencil. So we see graphically that it is continuous, and we should, using the formal definition, why it's continuous. Okay, and then part D. Problem D is a piecewise defined function, and so let's look at the three parts here. So if we look at step 1, does, not sure why that says m of x, we'll just use the h of x, the f of x. So does f of 1 exist? And so we're going to be testing this at x equals 1. So does f of 1 exist? Yes, according to this, when x is greater than or equal to 1, then we use this function, and so that's going to be 2. Requirement number 2, does the limit as x approaches 1 of f of x exist? And since, let's see, when x is approaching 1, this is, we have one function that we use when we're to the left of 1, and a different function that we use when we're to the right of 1. So to see if this exists, we need to separate this into two different limits, a left side and a right side. So we'll look at the limit. the limit as x approaches 1 from the left. When we approach from the left, when we're to the left of 1, that's when x is less than 1, we're using negative x plus 4. And then we want to see if that's the same as the limit as x approaches 1 from the right. And as we approach 1 from the right, now we're looking at x values greater than 1, so we use x squared plus 1. And so this left-handed limit is equal to 3, and the right-handed limit is equal to 2. These are not the same, so this limit does not exist. And since it does not exist, step 2 of our formal definition failed. This limit does not exist, and so we say f of x is not continuous at x equals 1, since the limit as x approaches 1 of f of x does not exist. Okay, and to see graphically why this is happening, our first function is the line negative x plus 4, so that has a y-intercept of 4 and a slope of negative 1. So it looks like this until we reach x equals 1, so it's actually going to look like this. So that's a line with a y-intercept of 4 and a slope of negative 1, and we use that whenever x is to the left of 1. And then to the right of 1, we have a parabola, x squared plus 1. And so that would be this parabola. But we're only using that parabola to the right of 1, and so it's going to start here. So when we plug in 2, we would get 5. So it's going to go through that point and continue upward like that. So we now see, oh, and it includes that point as well. And so now we can see why it's discontinuous at 1, because we have this jump. In order to trace along this graph, from left to right, I have to lift my pencil when I get to 1 to finish the graph. Anytime you have to lift your pencil, that creates a discontinuity. Okay, so I hope that helps you out with doing the problems on section 7.1.4. Just send me an email if you have questions.